Hello, my name is Martin Serra from Clarify, Argentina. I work on design and system verification, and I'm here today to present paper 19.3. Optical communication technology has been experiencing a paradigm shift towards coherent transmission and high spectral efficiency modulation formats. Coherent detection preserves amplitude, phase, and polarization information from the received signal, which allows penalty-free adaptive equalization of polarization mode dispersion and chromatic dispersion. The combination of coherent detection and DSP technologies allows costly optical signal processing hardware to be replaced by DSP-based technologies, and economical and large-scale deployments of coherent systems requires the transceiver to be implemented in CMOS. The transceiver presented in this paper is capable of transmissions up to 3,500 kilometers, and it's bundled with an analog front end, a DSP, a host and line transmitter, line and host receiver, and also line and host framer and multiplexers. Here we can see a simplified block diagram of the transceiver. It consists mainly of two parts, the egress and the ingress paths. On the egress path, data coming from the host is received by the host receiver, then passed to the egress framer, then to the encoder, and finally to the line transmitter. And data coming from the link is received by the analog front end, then passed to the DSP, where most of the signal processing takes place, then to the framer, and finally to the host transmitter. This transceiver has been evaluated on several optical links in our own laboratories. We can see here an example link tested. These links have included up to 1,000 kilometers of optical fiber, polarization scramblers, PMD emulators, and ASC noise. These tests have allowed us to mimic real-world applications of setups that can be found out in the field. Here we have a live demonstration of a 50-kilometer link, where the transceiver is both sending and receiving a test pattern. 50 kilometers of fiber is actually a short link for this transceiver, but we had to keep it short in order to reduce the complexity of this demonstration. So the transceiver has been implemented on an evaluation board, which can be seen over here, and uses a second board for power supplies and communication, and a third board for the optical devices. A tunable WDM laser over here drives an optical modulator and sends data through the optical link and through the 50 kilometers of fiber, after which ASC noise is added on a splitter, which is generated by an ASC noise source. Optical power of the signal and noise can be independently controlled by optical attenuators, allowing us to have full control of the optical signal to noise ratio level at the input of the receiver. After ASC noise is added, the signal is received by the receiver and demodulated by using a local oscillator and an optical demodulator. A custom graphical user interface that can be seen over here gives us full control of the transceiver, and it's actually showing right now the status of the multidimensional feed-forward equalizer coefficients together with the bit error rate in the ingress path at the line side. The bit error rate shown right now is around 1 E-3, which is the expected value for an optical signal to noise ratio at the receiver input of 11.3 dBs. Thank you for your attention.